I'm going to go over the homework first, and then we'll talk about some new things that you need to be able to do. So the homework was to start with 2 grams of barium nitrate and potassium sulfate and dissolve both chemicals in separate beakers with water. So what that means is both these chemicals then are aqueous. You don't even have to look it up because the description here says they're dissolved in water. So you mix the solutions in the 2 beakers and a precipitate or a solid forms. Now precipitate means something falls to the bottom. It's like precipitation with the weather. When the rain falls to the ground, that's precipitation. When the snow falls to the ground, that's precipitation. Well, in a liquid environment like water, when something falls out of that and sinks to the bottom, that's precipitate. So you're going to find the limiting, and I need to tell you that because that has to do with something you're doing in the lab and also the things we're going to be doing in future problems. So then you find the limiting reactant using the solid as the end product. So the first thing you have to do is balance the equation. And to balance the equation, you have to have balanced formulas. So you can see up here at the top that I have written down the charge on the barium and the charge on the nitrate. And I see that in order to be a charge balanced compound, I've got a 2 plus here and a 1 negative here. So I need 2 of these to have 2 plus and 2 negative. They cancel out and I get this formula. So barium, one of those, nitrates in parentheses because you put in parentheses polyatomic ions when you have more than one of them, and the 2 goes outside. And it's aqueous, we said. Then the potassium sulfate, potassium has a 1 plus charge, and the sulfate has a 2 negative charge. And I put a 2 here. It should be a 2 in front of the potassium. That's why I put a 2 down here. So that's a typo here. Please kind of ignore that, okay? The 2 should be in front of the potassium. Then over here, when I know these are 2 ionic compounds. I know they're ionic because I've got an ionic polyatomic ion in both, nitrate and sulfate. Anything with an AT ending or an ITE ending, those are going to be polyatomic anions. And so if you have an anion or any kind of polyatomic ion in the formula, you're going to have an ionic compound. If I got 2 ionic compounds like these, then you're going to have double replacement. When you figure out the products, you take the front part of this and put it with the back part of this, and you get barium and sulfate. And the front part of this goes to the back part of this. The front parts stay on the front. In fact, the positive parts stay on the front. The potassium goes before the nitrate here. You put them together. This is a 2 plus charge, that is the barium does, and the sulfate has a 2 negative charge. That's charge balanced already. I don't need any subscripts or additional subscripts here. The only subscripts that travel, you might notice, are those that are part of a polyatomic ion. So this sulfate, if you look it up on the common ions list, it's SO4 2 negative. That's what this looks like right up here. I'll write it in. So the 4 moves over because it's part of a polyatomic ion, but this 2 does not move over because it's not part of a polyatomic ion. This 3 moves over, it travels because it's part of a polyatomic ion, but this 2 does not. It's not part of the polyatomic ion. Well, the potassium has a 1 plus charge and nitrate a 1 negative charge, so this compound is balanced. And then you use, after you've got the formulas balanced, you leave them alone. Don't add anything or take any way away from the formulas. You only use coefficients to balance the equation. And I use an atom inventory. You must use an atom inventory on every equation, regardless of whether it's balanced or not, to show me that it's balanced. And then you use coefficients to get the numbers of atoms of each element to be the same on both sides. Then you're going to do the stoichiometry. So here's the mass-to-mass stoichiometry from the first product, the first reactant, the barium nitrate. Starting with 2 grams molar mass. I calculated the molar mass down here. I've shown you a couple of times how to do molar mass. Okay. And then you build the molar mass ratio here, the molar mass fraction, molar mass conversion unit to convert from grams to moles. Molar ratio comes from the balanced equation. It comes from the coefficients. In the case of barium nitrate and barium sulfate, because we're going from barium nitrate to the solid, that's the solid there, barium sulfate. There's a 1 implied in front of barium nitrate and the 1 implied in front of the barium sulfate. And so it's a 1-to-1 ratio. And then once you've got moles of barium sulfate, and you cancel as you go. You see I've canceled everything because I've already done the problem, because I've been going over this day after day. I hope you've figured out that by now. Then you're going to come up with another molar mass calculation, this one down here, in order to build this molar ratio, this molar mass ratio, this molar mass conversion unit, and convert to grams. And you round off using the system I've taught you, only looking at the measured or calculated numbers, these three. And this has the least digits, so my final answer needs to have 3 digits. That's the first mass-to-mass or stoichiometry problem. There are different types of stoichiometry, and one of those types is called mass-to-mass. All right, then we're going to do the stoichiometry from the other reactant, the potassium sulfate. Starting with 2 grams of that, molar mass conversion unit, molar ratio again, molar mass conversion unit, we find 2.50 grams of barium sulfate. So we've got 2 different masses of the product. The products on the right-hand side, barium sulfate is a particular product we're interested in here because it says we're going to find the solid. So if we look at these 2 masses, 1.66 and 2.50, this 1.66 grams is a smaller amount. If we look at what we started with, barium nitrate, that's a reactant. And this smaller amount here, 1.66 as opposed to 2.50, the 1.66 is smaller. That 1.66 amount of product tells me, that smaller amount of product tells me that the reactant I started with in that mass-to-mass problem is the limiting reactant. So I wrote down here that since the smaller of the 2 amounts is 1.66 grams of barium sulfate, barium nitrate must be the limiting reactant. And that's the conclusion you must reach when you do this problem. Okay? And that's the way it's done. That's the way we've been doing it. Now we're going to add something to that. We're going to start learning about the theoretical yield, and we're going to learn about percentage yield. Well, the theoretical yield is right here. This smaller amount of barium sulfate is the theoretical yield. Okay? So if we do these calculations, the smaller amount of product not only tells you what the limiting reactant is, but it also tells you what the theoretical yield is. That amount is the theoretical yield. Okay? All right. So let's move this into the camera view, and I'll show you how to use that. Okay, so here's the work I was just showing you, okay? And this is our theoretical yield. Now, what I don't have written in the problem already, but I'm using this as an example. This would be a theoretical yield because you can never get this amount. I mean, that's a theoretical amount. It's like the maximum. You'd like to get as close to that as you can, but you can never actually get there. That's because in the real world, in a real lab, in a real process to produce some product, there's always something left behind. You can't get a perfect amount out of it. We get really close, but we can't get that amount. So that's when we call it a theoretical yield. That's an upper limit. You can't get there. If you're taking calculus, you probably know what limits are. In calculus, it's a little more even. You get even closer to that, but you can't get into infinity. Okay, you get closer and closer and closer, but you can't get there. So the upper limit on the amount of product we can get is this amount. Suppose instead of that amount. So we're just coming up with a new kind of addition to the problem. Suppose instead of 1.66 grams, when we do this lab, we collect, let's say 1.25 grams of this solid, this barium sulfate. Okay? If when we do the lab, we actually collect this amount, then this then becomes our actual yield. That's actually how much we collect. Okay? That's the name of this. You need to make sure you commit to memory. Say it. I've been having you say things out loud in class. Say it out loud. Actual yield. the amount you actually collect at the end of a lab is the actual yield. And in the lab we're going to do, you will have an amount you actually collect. That will be your actual yield. It won't be barium sulfate, it'll be something else, but it'll be the amount you actually collect. There'll be an amount you'll predict through stoichiometry, and you'll have a theoretical yield in your stoichiometry. But when you actually do the lab, you'll get something less than that. If you get more than that, there's something wrong, because you can't have more product that you actually collect than is theorized through this stoichiometry. Okay? So what we're going to do is we're going to do the percent yield. Okay? So percent yield is calculated like this. You put the actual yield over the theoretical yield. Whoop, I can't even spell here. Theoretical yield. And put two C's in there. It should be one C. Well, once it dries, that'll be an A there. So THEORETICAL. If I can get it the white out to dry, we'll get that an A there. Sort of, kind of, maybe. There we go. Maybe. Oh, close. All right, you can see what I'm trying to do. I'll come back and do that later, maybe. All right, it's a theoretical yield. We're going to do that math. We're going to take the actual yield, divide by the theoretical yield, and then we're going to multiply by 100. That's the general formula for percent yield. That's always going to be what you're going to get, okay? Percent yield, okay? Or maybe I should put an equal sign over here. So in this case, this is our actual yield. So we have 1.25 grams of barium sulfate. That's our actual yield. We determined by discussing this that this smaller amount of the barium sulfate, the solid, is the theoretical yield. Well, that goes in the bottom. We need to do that math first, and then take the answer to that math and multiply times 100 to get the answer. So let's take a look at how this math works out. First of all, let's remember to cancel as we go. We have some units we can cancel out. Grams cancels grams. One on the top, one on the bottom, they cancel out. Barium sulfate cancels out. So when you do a percentage of anything, any kind of percentage, the units of measurement must cancel out. Sometimes the species, this is a chemical species, sometimes the chemical species will cancel out and sometimes not. So a little bit later in this unit, we're going to do what's called percent composition. And in percent composition, the species won't cancel out. But with percent yield, it does cancel out. The main thing is if percents are set up properly, units of measurement will always cancel out. If they don't, there's something wrong. Okay? So we're going to take that 1.25 and divide by, I know that's kind of, there's a glare on that, 1.25 divided by 1.66. I want to hit enter, okay, and I get this long number here. Well, the first thing is we have to multiply that number times 100, so times 100, and that's our unrounded percentage there, okay, our unrounded percentage. So that's, I've got 75.301, 204, 82. But I have to look at the measured and calculated numbers and determine how many significant digits to keep. This 100 is, that's an actually, you can't really call it a counting number. It's an absolute number. Okay, it's a defined number. So we don't use that for significant digits. Only these two numbers are used for significant digits. This one was actually measured. This was calculated. Okay, and so we have 3 digits in both. And we want 3 digits in our final answer, so we underline everything after the first 3 digits. Those first three digits are significant. The last, these 1, 2, 3, 4, 5, 6, 7, those digits are all insignificant. This is a percent, and we're going to round it off to 75.3%. Okay, that's the answer, but it's incomplete. Up till now with stoichiometry, you actually had the units and measurement still in the equation that weren't canceled out to find out what units to keep. In this case, it's a little more, you've got to do a little more thinking about it. What we've done is we've determined this theoretical yield of barium sulfate. Okay, so that's what you have to say this is. This is 75.3%, I'm sorry, not percent theoretical yield, percent yield, 75.3% yield. And you can use the word of, or you can use the word in, but I'm going to say yield of barium sulfate. That's the way you state what the percentage yield is. Okay. All right. So that's the only thing we're adding here. That's the new thing that we're adding at this point. So you got to calculate, be able to determine the theoretical yield. We've been doing that for a couple of days. Now we're just going to do percent yield. And to have that, you need an actual yield. And so when you read the problem, you have to be able to determine, well, what is the actual yield? When you do a lab, you have to be able to figure out what's the theoretical and actual yields, okay? And so what I want to do now is to go back to the slide presentation. Let's find a problem for you to do. Determine the percent yield of precipitate at 25 grams each of aqueous rubidium carbonate and calcium chloride are mixed together, and 10 grams of precipitate is recovered. There's a problem that has percent yield, okay? So you got to find the limiting reactant the same way before. You start with 25 grams of aqueous rubidium carbonate, 25 grams for the one stoichiometry problem. You got to balance the equation first. Got to balance formulas before you balance equations. So you balance the equation first. You balance the formulas before you can balance the equation. You do the stoichiometry starting with 25 grams of rubidium carbonate one time, going to the solid product. The precipitate is a solid product. Then you have 25 grams of calcium chloride. You start with that to find the solid product, the precipitate. And then if the actual amount, this is not what you're going to calculate to. When you calculate the theoretical yield or the limiting reactant and then get the theoretical yield, you won't have 10 grams. You'll have to have something more than that. Theoretical yield always has to be something more than the actual yield. And this is saying this is the actual yield. Okay? So that's the way we're going to do this.